time and so forth. So we have derivatives of logarithmic functions. So we'll just continue through, and we'll also have an opportunity in the examples we go through today to recap derivatives of exponentials that we did yesterday as well. So all those rules will come out. If we have y is ln of x, the derivative is 1 on x. If we have y is ln of f of x, the derivative is f dash of x on top of x. So straight away for our first example here, we have y equals 3x times ln x. So we should be starting to get into the habit of that there is a product. We have 3x times ln x, product, which means we have to use the product rule. So we identify u, and we identify v. We find u dash and v dash. So the derivative of ln x is 1 on x. And then we'll smash that together. Alright, so u dash v plus uv dash, and this could simplify to 3x times 1 on x, x at the top, x at the top. We'll leave it for now. Alright, over here we have ln of f of x. We have that whole function in brackets. So we should be looking at it like this. It's ln of that whole function there. So when we differentiate it, okay, well the function just becomes the denominator. We can go straight to dy on dx. What's the function there? Becomes the denominator. 2x. And the numerator is just the derivative of it. So the derivative of 3x squared will be 6x taken away 2. So that's a one-step differentiation. Go to C. We have e to the 3x take 2. And ln square root of x take 5. So this is intentionally sort of, we're drawing on a lot of rules here. We have ln of the square root of x take 5. The first thing I'm going to do is write that as a power. So we'll still keep it as y. And we should always, always, always be looking for places where we can apply the log rules, okay? Line them up here quickly. Okay, so we're going to be applying this third one here where we have a power. We can just bring that power out the front as a coefficient. So we have half there, and I'm going to bring it out the front of the ln, which is just going to bring it out the front of the whole thing, right? It's just going to be a number that's multiplying our whole answer. So half, we have e to the 3x take 2, ln of x take 5. All right, so I'm performing this in a drawn out manner as well. All right, so for our derivative then, what we'll do is we'll identify u. So u will be, now really it's up to you whether you include the u, the half in the u or not. It doesn't really matter as long as it's in the final answer. I'm going to include it. We're going to call that part u and that part v. So u is half e to the 3x take 2. V is ln of x take 5. All right, now, good habit, put brackets around your ln's, because if you write this, it's really unclear whether it's ln of x and then take away 5, or whether it's ln of x take 5. All right, so we must put brackets around our ln's. Okay, so we've got u, we've got v. Now we're ready to find u dash, and this is where we're recapping derivatives of exponentials, right? The half is going to hang out the front. Now, if we have e to the f of x, the derivative becomes f dash of x, e to the f of x. All right, so we just differentiate the 3x take 2, we get 3, that comes out the front, and we have e to the 3x take 2. For v dash, All right, we have ln of x take 5. Well, it's ln of a function, so the function is the denominator, and the derivative of x take 5 is just 1. All right, the derivative of kx is k, the derivative of 1x is 1, 5 disappears. Let's smash all that together. U dash v plus u v dash. All right, now I'm drawing out a rule here as well, okay? We're going to intentionally draw this rule out here because we're looking at that cubed root and we're going the cubed root, that means to the power of a third, right? So we could express this as ln of x to the 5 take away 2x to the power of a third. All right. However, this does not mean we can pull the third out the front because these are not the same. Okay, there's a difference between these two. Here is the circumstance where you can pull the power out the front. All right, that's because the power belongs to what's in brackets here. Over in this circumstance, what this means is it means ln of x multiplied by ln of x. It's ln of x squared, right? The power applies to the ln and the x, not just the x like it does in this circumstance. Now here, because the whole ln part is in the root, the power applies to the whole ln part, which means we can't pull it out the front. Okay. So we're going to have to use another rule here. So we're looking at it, and what we should see is we have something in brackets here. We have a function to the power of n. A function to the power of n. So that's the chain rule. Whenever we have something, a function to the power of n, we have to use the chain rule. Here's our function, here's our power of n. So the way we do the chain rule, okay, is we have n, we have the function, we have n take 1, okay? Those parts remain the same, n f of x, n take 1, and then we're multiplying that by the derivative of the function. Okay, so then we're required to differentiate this part. But you can see how the differentiation is compounding, right? Because if we're differentiating that, well, we have ln of a function. Okay, ln of a function goes to the denominator. Sorry, x to the 5, take 2x in the denominator, and the derivative of the function at the top. All right, so I'll just take you through that one again. We have a function to the power of n. We have to use the chain rule. N, our function, n take 1, the derivative of the function using derivatives of log laws. All right, so that's A, B, C, D. All right, question 2. Good. We definitely need to do question 2. So that's over the page. There's another one over the page. Are there any questions about the ones we've gone through yet? Excellent. Okay. So in question 2, we have ln of x to the 3 on x plus 2. And we're asked, show that the derivative is this. Okay, so this is one where we need to do the simplification. Now, a temptation might go, okay, ln of f of x. So then, like I think there's 2 strategies you could use to solve this, right? You could go, yep, so that's going to be the denominator, and then you differentiate it using the quotient rule to get the numerator. That's the long way of doing it. You can do it that way, but a lot of mathematics is going to be dedicated to what's the optimal process. And I said, and I'll say again, it pops up in one of the questions, I'll point out which one in a moment. If you can use log laws to simplify it, do. So we should look at that and then look up here at our log laws and go, which one of these does it resemble and can I simplify it? And it's this one here, right? We have ln of a on top of b. We have ln of one function divided by another. So we can reverse it. We can make it ln of x to the 3 take away ln of x plus 2. And now it is so much easier to differentiate. In fact, we're going to differentiate it in one step. Prior to that, if we were going to use the alternative procedure, we'd have to use the quotient rule. All right? Okay, so ready to differentiate. We're moving from y to dy and dx. Remember, we don't just have equals. Get rid of that bad notation. So ln, and even here, you can pull the 3 out the front. Like, they're going to be the same. Okay? But here we'll have, I'll show you why they're both the same. If we differentiate x to the 3, we'll get 3x squared, and the denominator is x to the 3. Alright, ln of x to the 3, there's the x to the 3 at the bottom, there's the derivative of 3x squared at the top. Now if you simplify this, right, what we have at the top is x squared and what we have at the bottom is x cubed. It would simplify to 3 on top of x. If up here, however, if we pull the power out the front first, if we wrote it as 3 ln x and then differentiated it, we would have 3 times 1 on x, which is 3 on x. Okay, so we're going to constantly see those connections. If you can use log laws, I encourage you to use them. All right, so we've got 3 on x, that's the first part. And the second part here is going to become 1 on top of x plus 2. So the function goes to the bottom, the derivative of the function at the top. Okay, so this is what we get when we differentiate it, but we're required to show that the derivative is this function here. They've presented us with a function 2x plus 6 on x squared plus 2x. So that means we need to bring these together somehow. We need to make them have the same denominator. And so we're going to cross multiply the denominators, right? We're going to multiply this term here by x plus 2 on x plus 2, and we're going to multiply this term here by x on x. All right, so just doing it slowly, on the left term we'll have 3x plus 2 on top of x times x plus 2, and on the right term we'll have x on top of x times x plus 2. They have the same denominator, so we can bring them together over the same denominator, and I'm even going to expand the denominator to get our same answer. We'll have x squared plus 2x in the denominator, and at the top we'll have 3x plus 6 take x, gives us 2x plus 6 on top of x squared plus 2x. QED. Alright, shown that it is true. Okay. So, yeah, that's a good introduction to logarithmic functions. So in your textbook, log laws, like if you read the questions carefully, so we're exercise 2G, what we'll start with today, it reminds you of the log laws. Okay, look at question 3. Use laws of logarithms to help differentiate. So that's where they're really going to start popping up. But in question 1 and 2, you're just finding the derivative functions using the logarithmic laws that we've had a look at there. So yeah, that's where we'll dedicate our efforts today. Derivatives of logarithmic functions.